Welcome to Applied Materials Engineering at Penn State DuBois. I'm Dr. Daudi Warioba, Associate Professor of Engineering and Coordinator of the BS Engineering Applied Materials option at Penn State DuBois. This option was designed to prepare materials engineer to fill the needs of the workforce for the powder metal industries. As you know, Santa Maria and surrounding cities are the hub or epicenter of powder metal industry in North American regions. Although we focus on powder metallurgy, we also offer a broad coverage of material science engineering in our curriculum. And these are built in the fundamentals of physics, chemistry, and mathematics. Some of the highlights of this program include a 100% employment record. Undergraduate students since from their sophomore year. We also offer internship in our local industries and conference participations. We have a healthy symbiotic relationship between the program and the local industries. They can use our facilities, and in return, they provide most of the tools and materials that are used in an undergraduate research as well as capstone projects. Our students are recognized for their work in the international conferences. This has also been another conduit for employment opportunities. Companies all over the nations, usually they visit the campus or call to inquire for our graduates, for opportunities to employ our graduates, simply because of what they had from the student in the presentation at the conferences. As I said before, we pride on hands-on active learning environment. You'll hear as a brief tour from some of our students of the facilities we have in our program, and you also hear from our alumni on how the program helped them to excel in their career. Finally, my colleague, Professor Ramakrishnan Rajagopran, will talk about employment and graduate opportunities that are available. If you have any question, do not hesitate to contact me.
Hi, my name is Dan Stauffer. I'm currently in my last semester here at Penn State DuBois. I'm in the Applied Materials Engineering program, and today I'm going to talk to you about powder characterization. Powder characterization is something that you want to do when you obtain a powder in as like a bulk sample. You want to test that powder for QC, which is quality control purposes. What we do with this machine here is it's called the master sizer, and that will give you the particle size distribution. So what you want to do is it pulls a vacuum, and you put your powder in the top here, and it sucks the powder down through as you pull on your feedstock here. It'll suck through the tube and then go into the master sizer. There's a blue laser that shoots across as the powder flows through. That powder is then measured through using refractive index of the blue laser. After all of the powder goes through the feedstock, it shows up here on the computer, and it'll give you a particle size distribution of what you just tested. So here we see it's between 10 and 100 micron. So what this is telling you is that the particles that you just tested were all between either 10 and 100 micron with a little bit of variation in between there. So what this does is gives you an idea of the size of particles that you're going to be working with. So when we look at different things in the video later on, you'll know that what you're working with to give the desired results of what you're ideally targeting through making your powder products. What I like about the Applied Materials program is that you are able to be in the lab every day if you want to be. It's more hands-on, and it's not just sitting in a classroom learning about this stuff. You actually get to use the equipment. So what we do is we'll come in through one of our lab classes and learn the equipment and then actually get to run it. I think that is definitely something that's an advantage to us because we're able to take that into industry then. With industry, I know that I had many advantages that I've learned from doing and using the equipment here. So I actually obtained an internship with Atlas Press Metals last summer after my junior year, and I was able to take what I've learned in a lot of my classes and actually perform different things that they do in industry. Without that, I don't think I would have been as successful, and all that success ended up leading to them offering me a full-time position this past January. So that was something that I took with a lot of gratitude to the staff here at Penn State, because they gave me the skills and the knowledge that I need to actually use in my future, in my career. I know that story that I've had is definitely something that a lot of prior students that have gone through this program have also experienced.
Hello, I'm Scott Coble. I'm a senior in the General Engineering Applied Materials option here at Penn State DuBois. During my time here, I've been afforded the opportunity to work with an adjunct professor here, Dr. Stephen L. Feldbauer, where we studied the lubricant removal process of powder metal components. During that opportunity has afforded me the privilege to present our findings at conferences and to be published in Thermal Processing magazine. So the advantage of powder metal is that you can take the powder and form it into a complex near net shaped component and center that part. So it begins with compaction of the powder. Here's a Gasberry double action press. It forms the powder in a die cavity to the desired shape and density. Now, there's lubricant that's been added to the powder that allows for the compact to be ejected from the die, and to bind the particles together, it is transported to sintering. This part is considered a green part at this time and has little structural strength, and if dropped, it will break. To gain structural strength, the part needs to be sintered. Here's our lab version of an industrial sintering furnace. The problem with sintering is the particles need to be in contact with one another, but the lubricant acts as a barrier. So the first zone of the furnace heats the component up to a temperature that allows the lubricant to melt, be wick from the part through capillary action. The subsequent zones of the furnace heat the component up to a higher temperature and allow the particles to be diffused together, giving it structural strength. Then the last zone of the furnace is a cooling zone that you could quench the part or allow it to be normalized. Also in the lab, we have secondary processing furnaces that allow us to do different heat treatments that are seen in the industry. This allows us to tailor the microstructure to meet the desired needs.
Hello, my name is Caleb Thompson. I'm a senior in the Applied Materials program here at Penn State DuBois. This is my last semester, and over the last 4 years, I've gotten the opportunity to work here in the Materials Characterization Lab for mechanical properties with all the machines in this lab, actually. One of the primary machines we use for testing here is what's called the Instron press. What this press does is it applies a tensile, so pulling, or a compressive, pushing load. We'll use something called tensile bars. We'll pull this apart until it breaks. We measure the force at which it breaks, and then later, once it's broken, we'll actually examine that fracture surface. This tells us a lot of information about the material and how it was processed. Now, something about this press is that it only applies what's called a static loading. So it moves very slowly, as you can probably see. So another thing we do in this lab is we apply something called dynamic loading, or very fast, like an impact. So for measuring things like dynamic loading or impact, we have this machine called the Sharpie Impact Tester. What it does is we take a bar like this, and it applies a very high rate of loading. So it swings through really fast as opposed to the other machine, which is much slower. It applies that load using this head, and it measures the difference in height between before and after the part is broken in order to determine the amount of energy used to break that part. And that can be used to tell us all kinds of things about how it failed, what the material was, and even how it was processed.
Hi, I'm Elena Keene, and I'm a senior at Penn State DuBois in the Applied Materials Engineering program. I chose this major because I have numerous job opportunities available to me, whether it be working with ceramics, polymers, or metals. Currently, I am working on my senior design project that deals with copper nickel silicon parts, so I utilize this room a lot. This is the metallography room, where we can cut, grind, polish, examine, and test the hardness of our powdered metal parts. The first step is to cut our parts. We have to cut our parts in order to view the microstructural differences with either an optical microscope or a scanning electron microscope. We have to cut them small in order for us to utilize them because our equipment cannot view larger samples. After the cutting, we mount the sample. We use this machine in order to mount the sample to give it a larger surface area as well as an easier time to polish. There are different mounting materials that we use depending on if we wanted to view it with an optical microscope or a scanning electron microscope. Once the mounting is completed, we move on to the polishing and grinding step. We grind the sample down to remove any irregularities in the surface of the part due to the cutting. We polish the step to further refine the part as well as give it a more reflective finish. In order to achieve this, we use different sizes of diamond suspensions. Once that is complete, we move on to etching. It is important to wear your safety goggles and gloves when handling these chemicals to protect yourself from the acids that we use. Once the etching is complete, we can move on to viewing it with an optical microscope. The optical microscope is able to view the porosities within the powdered metal parts as well as the defined grain boundaries. As for the testing, we have two machines here. We have a micro-hardness test and a hardness test. Both machines are useful in determining how well a sample is able to resist the permanent deformation caused from a harder material. The micro-hardness test is able to produce a small indentation at a microscopic level, while the hardness test is able to produce a much larger indentation that is visible to the naked eye.
Hey guys, my name is Nate Banner and I'm currently a senior in the Applied Materials Engineering program here at Penn State DuBois. Right now I'm sitting in front of the SEM, which is the scanning electron microscope. And how this microscope works is it shoots an electron beam directly at the sample under high vacuum. And the reason for this is so the electrons don't escape and it hits directly on the sample. Through doing this, we can examine the characteristic properties of the material. Some of the properties we examine are grain structure, grain size, grain boundaries, porosity, and the carbon content within the sample. Right here we have one of my projects that I'm working on for my senior year, and it's a copper-silver graphite sample. And what we're trying to do here is examine the composition within the sample, which we can see it's color-coded, and we're trying to examine the bonding that takes place within it. Through this equipment has the capability of EDS, which is electron dispersive spectroscopy. And that feature really lets us determine the composition within any sample we put in this machine. This enables the industry to come in here and we can troubleshoot whatever material they have and figure out exactly what the composition is, which really opens up a lot of doors for the students. A key feature here is that because the class sizes are so small, we have one-on-one interactions with the faculty. So I've actually had hands-on experience with this machine, which is very rare among any other university you go to. Because of the opportunities I've had, it's enabled me to apply to different industries, and it's also enabled me to get accepted into different grad schools, which I plan on attending.
Hi, my name is Lindsay Foster. I am a graduate student at Penn State University, pursuing my PhD in material science and engineering. I actually received my bachelor's degree here at Penn State DuBois in applied materials. Penn State DuBois has so much to offer to students, a lot of one-on-one time between faculty and staff with the students, where you get to really gain a lot of experience and training. One of the things that I hear a lot from students at other universities is they don't get the chance to touch any sort of equipment, but here at Penn State DuBois that's not the case. You're encouraged very early on to start getting some experience, getting some training, and that way you're well prepared by the time you graduate for a career, whether that be in academics or whether that be in industry. And one of the things that I really like specifically for myself is that I'm still technically working here with Penn State DuBois in the powder metal field. So I'm working with a lot of the undergraduates on their research projects. So they're getting some experience and contact knowledge for Penn State University through me, and I'm maintaining relationships with the students here and helping them along their way.
Hi, I'm Kevin Dixon. I'm a 2014 graduate from the Penn State DuBois Material Program. The program is unique in a few ways. First off, being size. The class sizes are great. They're smaller. You get more attention, more knowledge, more accountability. Secondly is the industry involvement. I've yet to see a program that is so in-depth with industry involvement. The professors know, they work in industry, they have worked in industry, they research with industry. They're setting you up for success when you graduate. Lastly is the professors in campus care. They're there to help, and you're not just a number to them. Skills that you learn from the program that really set you up for success are problem solving. You're going to use every day. Material properties, material analysis, research skills come in handy, and most importantly, professionalism. In my current career, I was a reliability engineer. Now I'm the reliability manager. I am in charge of a team of engineers and the heat exchanger reliability program at our refinery. The program set me up in a lot of ways for success, but most of all with the failure analysis. When we have things break, I can look at the cracks, look at everything that goes on, what impacts that. Did we set it up for success, or was it on our end? Material selection, if we had a failure or know we're more prone to failures, what materials should you use instead? Corrosion, erosion knowledge. Is it the crude sand that's causing us problems? Is it the coking? Is it a magnitude of things? Next is safety. So we have a very high safety standard. We have to. And the program set me up to know that the importance of that and the material selection involved with the safety. And lastly is the professionalism and responsibility. They teach you engineering ethics. Most schools don't still. And that's where it becomes really important to know as an engineer, my responsibility not just to the refinery, but to the people who work here. And Penn State DuBois material program helped me know that.
My name is Ram Rajagopalan. I'm an associate professor at Penn State DuBois. As you have heard from some of our students, many of our students work very closely with the local PM industries. And over the course of their study here, they get to know the companies really well, and eventually they get gainfully employed. We also promote many of our students to go towards graduate school. One of the things that we do is we engage them in summer undergraduate research, and many of them are also paid fellowships. And in this process, the students get to work on cutting-edge research, and some of them have been inspired to go on and pursue graduate school at University Park. Overall, we are a very closely knit family. We look forward to getting to know the students really well, and we also hope to see you here very soon.